What's up, students? Hope you're having the best day of your life today. Today, I talk about free body diagrams. We like to call them FBDs, and why they are your best friend when it comes to Newton's laws, specifically Newton's second law. I'm going to tell you when to use them and why, how to draw them properly, some mistakes that students make when drawing free body diagrams. And this is going to be good for anybody that's taking the SAT physics exam, AP Physics 1 and C. Don't really see it too much in AP Physics 2. You might, but not really. And anybody here in my home state that's taking the New York State Regents exam, this will be right up your alley as soon as you start dynamics and start to get into forces. So in kinematics, we talked about like the motion of objects and speeds, velocities, accelerations, changes in position, etc. But now that we're going to move into dynamics and Newton's laws, we are going to start to talk about forces. And a lot of times you're going to be given pictures of different masses and things like that. So here's like a mass on an inclined plane. Here's a picture of an Atwood machine that's you're going to see in AP Physics 1, just a box sliding on a surface, or even something in free fall. Now we're going to use free body diagrams to isolate different masses and explain exactly what's happening to each mass as far as forces are concerned, because sometimes it's not going to be that obvious. Now, for example, I can draw all the forces that are acting on this box. Say there's like a force of friction. We have the force of gravity that points downward. We have the force of the normal. But then if I want to talk about the forces on the table or on the inclined plane, you'd be like, what's going on here? Or even here. This box right here, it has a force of tension this way. It has a force of tension this way. But does it also have a force of gravity? See, it just becomes very, very difficult to identify. Which way do the forces point here? Well, we have a force of the normal. We have force of gravity. We might have some applied force that's pulling it. We don't know. Here, there's nothing really touching it, especially in our courses where we don't have air resistance. So there is just the force of gravity. Does that really get drawn onto this box? So the free body diagrams are going to allow us to take the particular item out of the system, treat it as one single point, then we can list all the forces and we'll be able to solve Newton's laws or identify if it's an action-reaction force pair in Newton's third law. So here are the steps to drawing a wonderful, perfect free body diagram and setting yourself up for success. The first thing that we're going to do is we're going to just want to draw a dot to represent the mass. This is going to do two things. Number one, it's going to separate it from the other objects that it's touching. And two, it's going to allow us to get away from like a weird shape. If this object was a weird shape, we wouldn't know where to draw the vectors from. We can just do everything as one particular dot. So I'm going to pick one of these drawings up here. I'll just do a very, very basic one for now, just so we can understand and we can go through the process. So let me just redraw one of these right now. And while I was erasing that, I realized that I want to do two because inclined planes, they always seem to trip kids up a little bit. So I just want to get you used to seeing inclined planes right away. So here's going to be a block on an inclined plane. And we'll say that there's an applied force up the incline. So I'll say there's a force up the incline. And there's also friction. Now the other one I want to do is I'll just do a very basic one. We'll have a force applied to the right with no friction. So for the first step, I'm just going to draw a dot to represent the box on the incline. And this dot will represent this box over here. Now, the second thing that we're going to want to do is we're going to want to draw vectors away from the dot to represent the forces. Now, I put this away here in bold because I want you to understand, if there was, say, a picture of something and the box was being pushed like this to the right, so the arrow came in and pushed this, in the free body diagram, we never have an arrow that comes into the dot. All of our vectors in free body diagrams are going to point away from the dot. So instead of drawing it towards the dot, I would draw this applied force away from the dot like this. This would be FA. So that's really, really important. And it's just going to make our lives easier when we're doing math and we need to figure out what's going to be negative. So never draw arrows into the dots. How do we represent what forces are going to be present? Well, we have to look at a couple different things. So here I've given you 4 different bullet points, and we'll go through each one and then we'll draw them. Anything that touches the object applies a force. Anything, guys. Ropes apply a tension force. They only pull and they don't get drawn in the diagram. A lot of times people want to draw ropes. We're just going to draw the vectors that represent the force of tension. Also, later in the year when we get to springs, springs are like ropes, but they can just push or pull, and they also do not get drawn. And they apply something called the restoring force. So we'll get to springs later in the year. Tables, ramps, floors, any flat surfaces may exert two forces. Not always, they may, and I'll explain the 2 times that they do and the other times that they don't. And then we have to think about things that have fields, like gravitational fields, electric fields, and magnetic fields. They're invisible, but they do touch the object, therefore they are going to apply a force. So if we go through each one of these, anything that touches the object applies a force. Well, we know that the surface touches the box, okay? And that force is going to be the force of the normal, which acts perpendicular to the surface. Now, also, we get to, this is a flat surface, so it may exert two forces. The other force it may exert is friction, and friction always opposes motion. So there's a force up the incline, therefore the force of friction, the second force applied by the surface, is down the incline, F. There is that applied force that's touching the object, that's pulling it up. So I'll draw that as F applied, F sum A. There's no ropes or springs. We already touched upon these. And is there gravity, electricity, and magnetic fields present? Yes, there is gravity, and gravity always points in the downward direction, FG. So these are going to be the 4 forces that act on this box. If I come over to this, we have a force applied, no friction. So this flat surface does not exert 2 forces, just one. And that one force that it does exert is up here. That is the force of the normal. Once again, the force that the table places on the object. And then also gravity is going to be touching this object, and it is going to point down with FG. And if I ask you, does Fn and Fg create a Newton's third law action-reaction pair? You should know the answer to that question. If you do not, you should go back and watch that video. The third point I want to make is that the length of the force vectors sometimes, not always, but usually represent magnitude. So I'll just give you a brief example here. If I had a box and I had a force that looked like this, Fa, and I drew a second one like this that looked like Ff, and I asked you if this box is going to accelerate, you would say yes, this box is going to accelerate because this force vector here is longer, therefore has a greater magnitude, so there'll be an F net to the right. If we have an F net due to Newton's second law, this box will accelerate. So sometimes you're going to see the length represented for very simple basic questions. Which way is F net going to point? You should be able to tell. They'll be obvious. They're not going to make it just a little bit shorter or a little bit longer. It'll be obvious. The next thing is that other vectors that are not forces do not get drawn onto a free body diagram. So common mistakes I see are acceleration and velocity. Students will try and draw those vectors on a free body diagram. Please, guys, you cannot do that. Also, inertia does not have a direction, right? The quantitative value of inertia is just as object's mass, and mass is a scalar. So we're going to make sure that we don't try and draw another arrow here and label that A, or another arrow and label that V. So the next point I want to make is exactly why I drew the inclined plane. We must define X and Y perpendicular axes and break anything into components that does not lie directly on those axes. So for this case, I'm going to call this right here the X-axis. And then perpendicular to that will be called the Y-axis. Over here, I will define this as my X-axis. Perpendicular to that, I will define this as my y-axis. Now we see all the forces act on an axis for this one. But right here, gravity does not act on one of the axes. So I must create components and find the components of this weight. Now, if you saw my video on inclined planes, you see that I'm going to call that force, that component, Fg, perpendicular. And that is going to be the cosine of theta, where this is theta. Then the other one I'm going to draw is here. That is going to be Fg parallel. Okay, now it's important to note that generally speaking, unless otherwise noted, components are not drawn on free body diagrams. Okay, so what I did here would be incorrect. I just wanted to show you where they'd lie. But on the side over here, that's where we'd find the component of weight. We would come over here and we'd solve for FG parallel equals FG, sine makes it slide, theta, and we would solve for FG perpendicular over here as FG, cos keeps it close, theta. They would not get drawn. Now, sometimes they'll say you could draw them, or sometimes they will explicitly say do not draw components. They do this on the AP exam a lot. They will say do not draw the components. But generally speaking, we do not draw any components of forces on our free body diagrams. The next thing we're going to do is find F net for the X and Y directions, and then use Newton's second law to find A. Okay, when we are using any of Newton's laws, especially when it gets to pulleys and things like that, rule number one, find A. If A is 0, great. If A is greater than 0, we need to know that immediately about the system. So the first thing we're going to always want to do is try and find A, and to do that, we must find F net. So for this first one, F net in the X direction is going to be equal to the force of friction plus the FG parallel, if I call down the incline positive, minus the force applied. F net in the Y direction is going to be equal to Fn, if I call that upward, minus Fg perpendicular. So although the components don't get drawn on the free body diagram, we still need to know those components to put them on there. And you could always draw your free body diagram off to the side, like your unofficial free body diagram that has the components on it. So you can see that these two are going to play together in the same direction, and it's going to oppose this one. For this box over here, we see that F net in the X direction is just the force applied, and F net in the Y direction is going to be Fn, if I call up positive, minus Fg. Then I could use Newton's second law of A equals F net over M. Given information about M, I could find acceleration of these systems. I have a whole video about just Newton's second law, guys, if you need to figure out how to solve for A. And I also have a full video about the force of the normal. This sometimes can be really, really confusing for kids. They think there's the formula to solve for Fn. There's not. You need to solve for it every single time. And in that video, I go through every single scenario where Fn is present and all the different ways you can solve for Fn. I'll try and link that at the end. The last thing I want to mention is that sometimes they're going to ask us to draw forces on the actual diagrams themselves. These are not free body diagrams, but I want to show you the difference between what they're asking here and what a free body diagram is. On the AP exam, I've seen this happen most often. So for this first picture over here, we'll call this picture A with the inclined plane in the box. I've seen them say, draw a vector to represent the force of the normal from its origin. So the whole year, we were doing everything from the center of the box, right? And kids would draw the force of the normal like this, and that would be incorrect because the point of origin, the force of the normal happens at the surface and it comes up through the box this way. So just be aware if they ask you to draw on diagrams from the point of origin. For another example, for rotation, an object spinning down the incline, the force of friction actually happens at the surface like this, right? Because the force of friction to get something spinning is actually a torque. So the force of friction would not be from the center of the object here. The same would be held true here. This would be the force of the friction if they asked you to draw that. So just be aware sometimes they're going to ask you to draw on the diagram. This is different than a free body diagram. Also, they'll break some other rules for free body diagrams to tell you that this is not a free body diagram. I've also seen them say, draw a vector to represent the acceleration of this object. So then in that case, you would just do this, but that's them explicitly asking for a vector of the acceleration. This is not a free body diagram. I hope that answers any question, helps you out with Newton's second law. If it did, give the video a thumbs up, leave some comments down in the comment section below if you have any questions. I'll catch you on the next one.